Yeah. I think it's 9:05 on my. Good morning, everyone. I want to welcome everyone to another multivariate statistics class. Of course, we are counting down to midterm two, and I'm actually going to say the midterm two will revolve around what we did the other time and what we're doing now. So. Specifically, I was going to revolve around multivariate hypothesis testing and the like, the last material that we work on before the spring break and the material we're starting this week. So this week, our focus is going to be on multivariate linear regression. Of course, in multivariate linear regression, I'm actually going to cover multiple linear regression. When I say multiple linear regression, we are trying to investigate relationship among variables, and we only have one outcome variable. And of course, what the focus is going to be on Wednesday and Friday is to focus on more than one outcome variable. But today, our focus will be on one outcome variable on so many predictors, so many dependent variables. And of course, if we want to investigate a relationship in statistics, we need to start with model specification. I'm actually going to walk you through how we specify our model in this regard. And whenever we specify model, we normally have assumptions, you know, because our model specification involve the error time. Okay, the when I say the error time, we're talking about the unexplained part of the model. So the assumptions will revolve around unexplained part of the model. And of course, if I really want to tell how good is the model, then we also need to investigate whether assumptions are good. I'm also going to walk you through the statistical inference on the model. When I say statistical inference on the model, I mean how do we estimate parameters in the model and how do we test hypotheses in the model? So in the estimation of parameters in the model, of course, we're going to talk about point estimation. We're going to talk about interval estimation. Then from there, we're going to talk about prediction, how if relationship exists between an outcome variable and some independent variable. So if I have information about independent variables, can I say something about the outcome variable, which we call prediction? And of course, I'm also going to walk you through individual prediction. We also have an average prediction. There's a difference between when I want to make an individual prediction and when I want to make a average prediction. And I'm also going to walk you through the uncertainty around that. Okay, I'm going to walk you through the interval estimation that has to do with individual prediction and the one that has to do with average prediction. Of course, this is actually what we're going to achieve today. Why on Wednesday and Friday we're going to focus on situation where more than one outcome variable is involved. Okay, so once again, I want to welcome you to multiple linear regression. Uh, this is actually very crucial in statistical world. I want to investigate whether variables are related. If I want to investigate that, I need to have an outcome variable. The outcome variable will be represented as Y. Okay, this is an outcome variable that we also call response variable. And of course, we're going to have one or more predators. One or more predators that we also call explanatory variables. Okay, So if you take a look at what I have, okay, I'm actually going to have one or more predators. Now, let me just tell you this. Whenever we want to study relationship between variables in statistical world, we normally start with model specification. So what you see right now is our model specification. We normally specify model, okay, whenever in statistical world. And the terms in this model, of course, I just walk you through what you understand. This is the outcome variable. Then this is the predictor variables. And of course, this is regression constants. Okay, that's a regression constant. And this guy, we're going to have a set of regression slopes. Okay, because we're going to have more. If I have more than one predator, I'm actually going to have more than one slope. If I have one predator, there's going to be one slope. If I have two predators, there's going to be two slopes. So the numbers of slopes that I'm actually going to have depend on the numbers of predators that I have in the model. Let me also say this. This part is a systematic part of a model, which we also call deterministic part. Okay, why this part is the error term, the error part. So that we also call stochastic part. Whenever we specify a statistical model, okay, particularly if we want to investigate relationship between some set of explanatory variables and outcome, we always our model specification can be in two parts. One part is deterministic part, while the other part is the random part that we also call stochastic part. Now, if I ask you to specify the model, I'm expecting you to give me definition all of this. Okay. I'm trying, when you take a look at this, I'm trying to tell you here that, okay, my response variable represent observations that will occupy a role in your data, and the observation value lies in real number. It could be any values in real number. It could be negative or could positive, it could be zero. So what this guy mean? This guy actually means real number. So if you what this one mean is the response variable is from real numbers. Okay, the response variable is from real numbers. Now I also said something the other time. The B naught also can take values in real number. The B naught that I call regression intercept, can actually assume any value. It could be zero, it could be negative, it could be positive. That's exactly what I mean. And of course, the BJ that we call the slope, okay, which is also going to tell us the contribution on average of each explanatory variable in the model. Also, lies in real number could take any form of values, could be negative, could be zero or positive, and also the random variable x, which are the features, also could take any values in real number. Okay, now this particular term is actually talking about assumptions that we impose on the model. Okay. And let me tell you this, if you are imposing assumptions on the model, you are imposing that on the random parts. In statistical framework, we normally impose assumptions on the random parts. And what is this assumption talking about? In the actual sense, if I'm talking about random parts, what do I mean by random parts? The random part is unexplained part of the model. Your model can't explain everything. Okay, a particular part your model cannot explain. That is the random part. Okay, and the assumptions here is actually assuming that that random part error must follow normal distribution with a mean of zero. You know what I mean? The mean of zero actually means on average, unobserved effect. Okay, on average, unobserved effect is zero. That's why you don't include them. That's why you don't include them in your model. So this part, please pay attention. This part is actually unobserved factor, something that you did not observe. And why you did not observe them? Because you believe that they have a minute effect. Because what this guy is trying to tell me is that on average, this one saying expectation of the error, expectation of the unobserved equal to zero. What I mean is because the effect is negligible, and that is why it is omitted from the model, and that is why it is not observed. Does that make sense? And we also expect the unobservable effect to have a constant variance, sigma squared. Okay, so the error the assumption we're imposing on this model now is trying to say that the unexplained parts should have a negligible effect on average, and not only that, they should have a constant variance. You can only trust the model if and only if the assumption hold. The moment the assumption is violated, you cannot trust the model. That is the specification now. Now I'm moving now. Okay, now I want to consider, when you talk about multiple linear regression, we have a special form of a multiple linear regression. So what if in a situation where you have only one predator and you have one outcome? I'm going to say that again. When you have one predator and one outcome variable, that becomes a simple linear regression. Okay, maybe I'm trying to look at the effect of weight on height, or I'm trying to look at the effect of mother's weight on daughter's weight. Okay, I'm looking at the effect of one variable, okay, on another one variable. That becomes a simple linear regression. But situation, so which is what I'm describing here. Take a look at that. If p equal to 1, if I have one explanatory variable, I have one predator. Okay, the one predator may be weight. Maybe I'm looking at the effect of weight on height, where height is the outcome. Of course, that situation p equal to 1. But what if in this situation, I'm actually going to have the model is going to change. So just beta naught plus beta 1 x, okay, plus the error. The model is going to change to that, because I'm only having just one predator. If I have one predator, I'm actually going to have just one slope. Okay, so take a look at that. But situation where we have more than one predator, we want to consider this now, where the number of predator is more than one. I remember what I did. One of the when I was in undergraduate in Nigeria, I think I work on the effects of exchange rates, inflation rate, and grow on the consumer price index on the gross domestic product of Nigeria. So which means I'm looking at the effect of three variables on just a single outcome. That's a multiple linear regression, which is what I'm describing here. In that situation, I'm actually going to have several slopes. The beta 1 to beta p here means the numbers of slope you're going to have depend on the numbers of features. Of course, in any of this model, or whether simple linear regression model or multiple linear regression model, you're still going to have intercepts. Does that make sense? You're still going to have intercept beta naught. Don't forget that intercept is just talk about the mean. We want to talk about the mean of the response variable. Okay, please pay attention. Statistics is not hard. I think what makes statistics to be difficult to students is when students don't pay attention to they don't pay attention to the terms in the model, because whenever we want to investigate stuff statistically, or we normally specify model. So if I were you, you need to be able to get yourself familiar, or what is the meaning of each term in a model. Okay, the meaning of each notation, which is what I'm actually explaining right now. Okay, so I'm actually going to say in general the we have a regression model where we're actually going to relate the response variable as a function of predators. Okay, and when I say predators, I mean x1 up to xp. Now, let me tell you this. What makes our statistics to be unique? What makes statistics to be different from other uh, field is because of the fact that if we want to investigate relationship or we want to seek redress using statistical framework, we normally start with model specification. Okay, we know the model. The model that we specified ahead of time is actually our thoughts about about how things should work. Okay, and whenever we specify a model, assumptions always start with or always come with the specification. Please pay attention. Whenever we specify a model, assumptions always come with the specification. And when assumption comes, what are these assumptions? If I want to talk about, when I say MLR, I mean multiple linear regression. Okay, I wanted to see the word linear. I'm assuming a straight line relationship, a straight line. So in the first assumption, okay, I have to tell the world that the relationship between the variables under investigation should be a straight line relationship. That's what we mean by linear. Okay. And not only that, uh, we have to tell the world that we have observed some random variables. We have outcome variable, we have predictor variables. And not only that, we're also going to talk about assumptions underlying the error, the assumption underlying the model, the fact that we're trying to say the error should follow normal distribution with a mean of zero and a constant variance sigma squared. Let me tell you this. We have a way to investigate this because whenever we estimate parameters using model that we specified, before we can tell on whether the model is going to do a great job, we need to have a way to investigate if assumption hold. This is synonymous. This is synonymous with a situation whereby before a court we entertain a case. A court will need to for force verify that they have a territorial jurisdiction to entertain a case. Okay, there's a particular scenario that I normally cite as an example. Somebody committed an offense in the state of Minnesota, and the person ran to Philadelphia in state of Pennsylvania, and the court in Pennsylvania, they tried this person and confirmed the fact that he committed a crime, and this person was prosecuted and was jailed. Uh, I'm actually going to tell you they are not doing the right thing. Whatever decision they take will be declared null and void. You know why? Because the person did not break the state of Pennsylvania law. The person broke Minnesota law. So if they want to do something that makes sense, that person should be repatriated back to Minnesota and be tried using the law of Minnesota. The same thing here. The same thing with a model. Okay. If I really want to know, before using a model in policy formulation, we need to first investigate whether assumptions underlying the use of this model met. If the assumptions are violated, you're actually going to mislead. We don't want to mislead. Okay, now we also believe that we got parameters. These are regression parameters. If you look at what I circle now, they are regression parameters. When I say regression parameters, I actually mean regression constant, beta naught, and the regression coefficient. The regression coefficient is beta 1 to beta p that we also call regression slopes. While the beta naught is regression constant, all of them together, we actually call them regression parameters. So we believe that as at the time that we specify the model, these regression parameters are unknown. We don't know them. But we believe that when we have our data set, they can be estimated. Does that make sense? There's a lot of story here. I understand my statistics perfectly. I understand my mathematics perfectly because I always understand, trying to make sure I understand story behind every notation. That's a story. Okay. Now, the last assumption. That is very, very crucial. Please pay attention. You know, if you look at assumptions in number three, let me tell you this. The moment the assumptions in number three hold, the moment error follow normal distribution. You know what I call error the other time? The error is unexplained part of your model. A model cannot explain everything. So the part that your model cannot explain is a random variable that must follow normal distribution. If that assumption hold, then the consequence of that assumption is that your response variable will also follow normal distribution. So if you take a look at assumption number 5, the response variable, which I call the outcome variable, it is required that it must follow normal distribution. But it can only follow normal distribution if error follow normal distribution. If the assumptions in 3 hold, assumptions in number 5 will automatically hold. And let me tell you this. What is the similarity between number 3 assumption and number 5? Okay, number 3 is focusing on the error, is focusing on the unexplained part of the model. I remember when George Box said, and I quote, all models are wrong, but some are useful. Why did he come to that conclusion? Why do you think George Boss come to the conclusion that all models are wrong, but some are useful? Because when you ask a question whether a model is true, if you mean a whole true, the model is not true. I'm going to say that again. If you ask a question on whether a model is true, if you mean a whole true, the model is not true. Because model cannot be completely true. And that is the reason why we have a place on unexplained. Okay, a model does not give exact characterization of reality. A model gives an approximate reality. Because of that, and that is why in the model we're always going to have a random part that we call the unexplained parts. Now here we're trying to say, please pay attention. We're trying to say, if I have a response variable which is condition, this guy me, condition on the predators. We have a response variable, condition on predators. Okay, the moment error follow normal distribution, the moment this guy hold, then this guy will also follow normal distribution. With the mean of this, look at that. This mean, take a look at this mean. Oh my God, the mean here is just the systematic parts. You know why? Because when you go back to the model where we specify the, please pay attention. What I'm explaining now is very, very critical. Initially, the model specification is actually this. The model specification is actually this. The model specification is actually what I have here now. Okay? It's actually what I have. The model specification involves both the systematic parts and the random parts. But when the response variable condition on the explanatory variable follow normal distribution, the mean of that is just going to be systematic parts. You know why? Because when you take the expectation of both sides, okay, when you take the expectation of both sides, Okay, because this guy actually implies that expected value of error equal to zero. Okay, therefore the error is not going to be part of the model anymore, and that is why you have the mean of the response to just be systematic part. But you know what is the similarity between number three and number five? They must have the same variance. Error followed normal distribution with sigma square as the variance. The response variable also followed normal distribution with sigma square as the variance. They got the same variances, but they got different means. The error has a zero mean. Then why the response variable has the mean to be systematic or deterministic part of the model. Is there any question here? Is there any question here? Okay, that's a very good one. Oh, I think I forgot to say this. There was a time we had a lecture on Zoom, and I said my daughter was involved in a signing. You know, she does sports. She was actually uh, she was taken in three university: Canton State, Minnesota State, University of St. Thomas, University of Minnesota. But my daughter has finally committed to University of Minnesota. And I just want to give you the story. So from the beginning. Okay, now I'm actually gonna move right now. Let me see. Okay, now we want to go into matrix form. What are we doing here? You know, there are some questions that uh students of math, student of statistics should ask. I asked that same question when I was in college. Now, the very first question I'm going to ask, what are we doing here? Oh, what we're doing here is we want to have our module specification in matrix form. We want to have what we have here before. Please pay attention. What we have here. Can you see that? This guy, this guy is a module specification in a scalar form. This is not in matrix, but we always find it very easy to work with matrix when so many variables are involved. And that is the reason why we actually want to specify our model in a matrix form. So I want to welcome you to this. Okay. This is a model specification in a matrix form. When I ask you in exam and I ask you to state multiple linear regression model, okay, uh, I think I need to be specific, because you can decide to state the multiple linear regression model in a scalar form or in a matrix form. But if I'm going to be specific, I can say, okay, can you state that in a scalar form? I expect the other one. If I ask you to state that in a matrix form, I expect this. In a matrix form, Y is going to be a matrix. It's going to be n by 1 matrix of observation. X, that very X, is actually going to be a matrix as well. That's what I'm defining here. Please, I need you to pay attention. If you take a look at this guy now, because I want us to understand every time, every notation used. Statistics is very easy, but what is making it not to be attractive depends on if you don't pay attention to the story program behind every notation. I told you the other time I understand all this because I know what each notation represents in real life. You know what this Y is what he's talking about? He's trying to say, oh, the particular Y that I have in this model now is actually a matrix of n by 1, which is for observation. Okay, and here lies in n-dimensional space, which is depending on the number of observations that you have. Okay, and you know what? Please, if you don't understand, you ask me a question, whether you are in person or online. Now look at S. That's a design matrix. You know, we are expecting that to be n by p, number of observation by the numbers of features. But we also need to incorporate intercepts. And that is why, if you please pay attention, take a look at this. These are the features. This is the intercept. 1, 1, 1, 1, 1, 1. That very one subscript n means I'm going to have 1 in n time because I'm incorporating the intercept. Because of that, the dimension is now is going to be, instead of it to be n by p, but it's going to be n by p plus 1. The plus 1 is actually the intercept. Okay, now we're going to have, this is going to be the regression parameters. The regression parameter is going to be b naught, then b1 to bp, which is going to be p plus 1 by 1. Okay, p plus 1, y plus 1. You're also estimating the intercept. Does that make sense? There's a lot of story here. Now, I'm also going to have the error. I need you to pay attention. There's something that is similar. Please pay attention. Take a look at this too. Mm. The error and the response variable, they have to be in the same dimension. Does that make sense? You remember the other time when I was talking about absorption, when I said implication of, when the absorption revolving around the error hold, when error followed normal distribution with the mean of 0 and the variance sigma squared, then the response variable will also follow normal distribution. It is required that when error followed normal distribution, the response variable should also follow normal distribution. So the two of them has to be in the same dimension. Okay, if the response variable is n by 1, the error should also be n by 1. You know where the error is coming from? The error is going to be a distance between what you observe and what your model suggests. That is the difference between actual response minus predicted response. Actual response is y, predicted response is y cap. Where do you get your predicted response from? From the model. That's what your model say. Okay? So that is why. Okay, now I'm actually moving now. Now, this is now giving you the matrix. If you specify multiple linear regression model in a matrix form, you're trying to tell the world this is your matrix Y. Okay? This is for the X. I told you the other time, even though this is my X1, X2, up to XP, but I'm also need to incorporate a constant of 1, 1, 1, 1, 1 to incorporate intercepts. Does that make sense to everyone? Okay. Now, do you know that this, I'm rewriting that in this form? Look at that. I'm rewriting that in this form. Okay. And if you're not going to see that this particular guy here is just this guy minus this guy. Does that make sense? The response minus the model. This is what the model suggests, which is the deterministic part. So this minus this will actually give me that. So this is what the model cannot explain. Errors. What the model cannot explain. Okay, now I'm actually moving now. I'm moving now. Now, just like the way we specify the assumptions of the error in where we have a scalar presentation, we're also going to have the assumptions of the error when we actually use matrix to reflect a multivariate normal. Take a look at that. That's multivariate. That's multivariate. Now, please pay attention. Do you know the other time when we have the model specified in a scalar form, I said the error must follow normal distribution with a mean of 0 variance sigma squared. And I said the implication of that is that the conditional distribution of the response given the predator must follow normal distribution with a mean. The mean is going to be the systematic part of the model, and we're still going to have a sigma squared. But I'm trying to state the assumptions again when the model is now in a matrix form. When the model is in a matrix form, that is going to be the distribution of the error. And that would be the oh my God. If you take a look at what I have here now, is the one that is representing this. You remember this the other time when I said beta naught plus b bj, sj. Okay, this guy is just the scalar form of that. This is the matrix form of that, and the sigma square. You remember I said that the other time? Okay, so this is just having the absorption reproduce when this model specification is actually in matrix form. I want to move right now. Now, the question now is, what method are we going to, if I have my model specified, okay, and how do we estimate the parameters, the regression parameters in a model? We have several methods that we can use. We have a method of ordinary least squared. We have a method of maximum likelihood. But you know what? I want to show you the method of least squared. Now, in the method of least squared, don't forget, please pay attention. Take a look at the model. This is the model, right? Now, you know what I want to estimate in this model? I actually want to estimate B, which is this. I want to have, because if I were to measure relationship between variables and an outcome variable, I need to first estimate the regression parameters, which is actually going to be the contribution of each of the predator to the response, which is going to be the one I want to estimate beta naught to beta p. But if I want to estimate beta naught to beta p, then I have to do that in a way that I will minimize the error. If I want to go by here, what is the error now? Error is going to be y minus xb, right? Now, I need to use an approach that will minimize the distance. Okay? I have to use an approach that will minimize the distance. And that very approach is what we call least squared. Now, pay attention. You know what we know what we're doing here? We want to minimize this gap. We want to minimize the square of the distance. Why are we squaring? Mm. You know, this guy itself is the error. But we want to tell the world, if the error is a -3 and error is 3, they are the same in terms of in terms of, not in terms of magnitude, in terms of the way it is from to zero. It's just like I have this. It's just like I have this, and the center is 0 here, and here I have a negative. I got a -3, and here I have a 3. Do you know that the distance from here to here is the same as distance from there to there? And if I want to tell the world that, okay, the distance is the same, I can square them. When I square -3, that give me 9. When I square 3, that also give me 9. And that is why we're squaring this. Can you see that? And when you squared, we want to minimize the square. And that's why it is called least squared, least squared. Okay? Now, we're now going to use the approach of optimization here. If you take a look at this, I actually want to get B. What is my B? Okay, P plus 1. B now B1, B2 up to BP. Okay, and here I'm rewriting the equation model back in a scalar form. Okay, now I'm now in scalar form. Okay, now if the way it is now, I'm actually going to use optimization technique where I'm actually going to, let's say if I call this guy L, then I'm going to do the L, okay, the B naught. I will do that, the A, the B1, the A, the B2, and so on like that. okay? And in the end, because this is applied multivariate statistics class, I'm not going to show you all of that. We don't need that. But what I'm really going to tell you is that this is the way, this is what I'm actually going to do. You know, with this, if I do that, I'm actually going to have access to my beta naught cap. I'm going to have access to beta 1 cap all the way, all the way to beta p cap. I'm actually going to have access to that. So this is the formula. Okay. Now, what would I just need is just to play around matrix multiplication or inverse or transpose that we've talked about before. So this is the OLS formula. Okay. That is the OLS formula that we're going to use. Okay. And like I said, the formula is this guy is going to give us all the parameters that we need. Is there any question on this one? And this is going to be easy. You know why it's going to be easy? It's going to be easy in the sense that, you know, if you have your X, I show you your X the other time, you can find S transpose. Then you can do S transpose multiplied by S. You can do the inverse. You can do the inverse. Then you can do S transpose multiplied by Y. Then when you do that, then you multiply that guy by this one, and that will automatically give you that. And that was why, where we this one come from? That was why I was showing you this at the time based on your data. Look at that. That was why I was showing you this. This is your Y. This is your design matrix X. This guy is your design matrix X. This is your Y. Okay. This is the B that we want to find. Okay. And this is the error. Take a look at that. Does that make sense? You know, at the moment you have your data, you actually going to be fine. Okay. Now I'm moving out. I'm moving out. Now the next thing is after getting my regression coefficient, after getting this, do you know I'm now ready to make a prediction? Okay. I've gotten this. I've got a beta cap. Do you know in a scalar form, all of this, please pay attention. This guy is this in a scalar form. You know what this guy is trying to say? Maybe after getting the results, I'm just assuming now, maybe this is 3. I'm just assuming plus 6x1. I'm just assuming plus 3x2. I'm assuming that, okay, maybe minus 7x3. Okay? I'm just assuming. So here is maybe you have 3 variables and you've estimated this is your beta naught. Okay, this is your beta 1 cap, you know, the estimated. Okay, the estimated, and this is your beta 2. I'm just assuming this is your beta 2, and this guy is your beta 3. Of course, if you know any value, if you know the value of x1, the value of x2, the value of x3, you can now make a prediction. Y cap is a predicted Y. Does that make sense? That we also call fitted. We call it predicted. We also call it fitted. So this is in a scalar form, and why this is in a matrix form. And let me tell you this: the moment you have your fitted Y, which is a predicted, you can find the error. Okay, that we're actually going to call that residual. What is the difference between error and residual? Error, they mean the same. The two of them is talking about difference between what I observe, okay, and what I predict. But let me tell you this. We use error. When I talk about error when we are working with the population of data, but we talk about residual when we're talking about sample. We always work with sample. Does that make sense? Now I needed to pay at oh my God, you know, the residual is just going to be the difference between the original. Look at this. There's the actual response and the predicted response. The difference between them is what we call residual. Does that make sense now? Okay. When you have fitted, from fitted, you'll be able to have residual. Does that make sense? Okay. And you cannot have fitted if you don't have B estimated. And of course, you're going to estimate your B using this. Now I'm moving now. Moving now. Now I want to go into art matrix. I'm going to stop at art matrix. Of course, I said we're gonna do this. Today we're gonna do this on Wednesday, and of course the other one on Friday. Now let's talk about art matrix. What is the significance of art matrix? And how can I derive art matrix? Please pay attention. It's very easy. If I have this as a fitted, right? And I plug back in the B cap. You know, the other time I said from the OLS, this guy is actually this. You remember the formula? Now, when I plug that in, I have this guy now. When I have this guy now, please pay attention. Okay, this part, the part that does not have to do with the response, a part that does not have to do with Y is the art matrix. So that guy is H, which is what I'm writing here. Okay, but do you know where there's going to be an exam here, exam question here? Please pay attention. Because without art matrix, there is no way we can transform the actual response to predicted response. I'm going to say that again. Without art matrix, we will not be able to transform actual response to predicted response. Actual response is Y, predicted response is Y cap. Now, before we'll be able to transform that, we need to investigate. We need to investigate properties of our art matrix. Art matrix has to be idempotent. Idempotent is if I use it to multiply itself, it's going to give itself. Look at that. If I have this guy, X, this, transpose, please pay attention, S, transpose, multiplying itself now, okay? If you multiply itself, it's going to give itself. Well, let's see. Take a look at this. This guy, we cancel this guy. What do I have? I see have this guy back. That's what I'm trying to talk about here. That's what we mean by it is idempotent. It is also symmetric. You know why symmetric? Symmetric means if I find the transpose of an art matrix, it will also give me art matrix. If I find the transpose of this guy here, if you find the transpose, it's still going to give itself. The moment that hold, then this art matrix will enable us to project the actual Y onto the column space of X. When you do that, then you'll be able to have a prediction. So that is the job of art matrix. The art matrix enables us to project the actual response onto the column space of X and in a way becoming a predicted response. Now, this is how to do it in R. I have, I have my data set and, this is the code. Here, Y is the MPG. I have 3 predictors. Look at that. Now, how do we automatically give you all what I need? Look at that. This is the B naught. This is the B1. This is the B2. This is the B3. This is the B4. How do we automatically give you? This is the data frame. Look at that. And this is the coding now. If I were you, why can't you try that coding out? What are we going to do on Wednesday? Where are we going to start from? We're going to start from how we can decompose variations around the response variable to explain variation and unexplained variation. That is where we're going to start on Wednesday. Is there any question before I go today? That's all I got. Make sure you all stay safe and have a lovely day. Bye for now, everyone.